Okay, so thanks everybody. I can't see you, so if you need me to stop or repeat anything, please just unmute yourself and butt in. Don't bother raising your hand. Please do feel free to butt in at any point. You can see from the title that I'm going to try and give you a bit of an introduction to machine learning applied to fluid dynamics. This is basically a presentation that I gave. Well, I've modified it quite a lot actually, but it's based on a presentation I gave to the Leeds Institute of Fluid Dynamics Machine Learning Study Group, and we had a session in October, and I used this paper called Machine Learning for Fluid Dynamics, which is in Annual Review of Fluid Mechanics by Brunton et al. And I sort of used this to summarize their review of state-of-the-art in machine learning for fluid dynamics. So you'll see I've borrowed from their paper a number of their diagrams, and so whenever you see a diagram or a figure number, it's direct reference to that paper. And I've also deliberately tried to just take out lots of quotes from the paper to sort of make the point. So you'll see lots of quotes in this presentation which are directly taken from the paper. So yeah, this is what I'm trying to do, give you an introduction to the role of machine learning in fluid dynamics. I'm going to try and cover all of the following topics. So a little bit about some of the taxonomy and language that's used in the machine learning community, and you'll see the acronym ML for machine learning. I'll introduce you to some of the fundamentals, and then I'll very quickly introduce you to three different families or types of machine learning approach: supervised, unsupervised, and semi-supervised, although because I've not given this talk before, I'm not sure for how much time I'll have for that bit. And again, you'll see NN is going to be an acronym for neural network that I use throughout. And I do want to make sure that I give you a little bit of a discussion of some of the applications in flow modeling and in flow optimization and control. So these are two different application areas. One of them is specifically using machine learning to model flows. The other one is using machine learning to perhaps control or optimize flows. And so I'll try and make that distinction. And I'll finish with a discussion including some of the open problems that we need to address in the fluid dynamics community. So this diagram is figure 1 in their paper, and it basically gives an overview of some of the types of machine learning algorithms that exist, and classifies them into 3 groups: supervised, semi-supervised, and unsupervised. So as you've already seen from my introduction slide, I will try to explain what those things mean in the course of this presentation. And then underneath that, it kind of gives different, I'm not quite sure if they're intended to be applications or types of algorithm under those headings. It's a bit of a mixture, to be honest. It's mainly types of algorithm, but some applications. So classification is a term that's used in machine learning. That's one of the original applications of machine learning was to solve classification problems. So that might typically and historically have been, if you show me a photograph and ask me the question, is there a cat in this photograph, or is that a photograph of a dog or something like that, to be able to say yes or no, or to be able to say, here's a photograph, is it cats, dogs, or neither. So classification could be binary, ternary, or more sets. But grouping things into sets is a classification problem. In fluid dynamics, that might, for example, be, is this a turbulent flow or is this a laminar flow? And can we tell from an image, and can we train a computer to determine from a video or an image what type of flow we're looking at? Regression is just a generic name for, can we find a relationship between independent variables and dependent variables? So we have some inputs and some outputs, can we find a relationship between the two? So clearly this is a really important feature of machine learning, because a lot of what we do is regression. And actually, I've just looped in this slide some of the things that I'm going to touch on in this presentation. And in their figure 1 in the paper, they put neural networks under classification, but actually I'm going to focus mainly for neural networks under regression. And then there's this set of algorithms then which come under this semi-supervised heading, optimization and control. So that's an application area. So this is about how can we control the inputs to a flow problem in order to optimize something. So for example, that might be we want to minimize the drag around an aerofoil, or we want to maximize the downforce on a Formula One car. So we're trying to control the inputs. That might be the geometry, that might be the flow speed or something like that. And we want to choose the inputs that achieve some objective, maximizing the downforce, for example. So that's an example of an application. But the other two things headed under the heading semi-supervised are examples of different types of semi-supervised learning algorithm, and I will briefly touch on those in this presentation. And then for unsupervised learning, there's applications which are listed here: clustering and dimensionality reduction. I'm not going to I've actually dropped a little bit on k-means clustering in the presentation because I know I wouldn't have time to cover it, but I will talk about proper orthogonal decomposition, POD, and principal components analysis and autoencoder as an example of unsupervised learning. So this is kind of a whole view of the different types of machine learning strategy: supervised, unsupervised, semi-supervised, and I'll explain what they mean over the next few minutes, and then a whole range of different either applications or types of algorithm fitting underneath these headings. And the things I've circled here are things I'll touch on in this presentation, although I should have uncircled k-means. But I'll touch on them in different levels of detail. I'll focus primarily around neural networks. I'll spend a little bit of time about deep model prediction and a little bit of time on dimensionality reduction. So what is machine learning? So this is a quote from their paper. Basically it says that the learning problem can be formulated as the process of estimating associations between inputs and outputs, possibly also parameters of a system, using limited observations. So what does that actually mean in practice? So let's ground that in fluid dynamics. Imagine we are interested in a steady flow. Okay, let's keep it simple: a steady, incompressible flow. So what might the inputs to our system be? Well, the inputs might be boundary conditions and the geometry. So for a given set of boundary conditions and a given geometry, what is the flow field? So the outputs might be the velocity field and the pressure field at different points. That might be the centers of a finite volume mesh, or it might just be arbitrary collocation points that are selected around the flow domain. So inputs would be the things that control what that flow is: geometry, boundary conditions. Outputs would be the flow itself. And the learning problem in this case would be, so can we formulate some sort of model which for the given set of inputs correctly predicts the outputs? And in this case, there might be some parameters in the system. So for example, we might have the Reynolds number as one of the parameters or something like that. Or you can think of it as an input. And then how are we going to achieve that in a learning system? So I'm assuming you can see my mouse on the screen. Please shout if you can't. So the way we're going to achieve that is we're going to introduce a learning model or a learning machine phi. So phi is going to be a function which relates inputs x and outputs y. And the idea of this function is it will give us an approximation to the system that we're trying to model. So I'll call that the ground truth. So in our case, ground truth might be not what you think ground truth is. So in our case, ground truth may not be the reality in the physical world. In our case, ground truth might be the output of a really high resolution, high fidelity CFD calculation. So we might say ground truth is whatever ANSYS tells us the flow looks like when we solve on a mesh with a 10 million volume elements in our finite volume mesh. So ground truth doesn't necessarily mean what it should mean. It means whatever it is that we're using as our representation of the real world. So X would be input. So in this case, our inputs might be, for example, as I said, the positions of the boundary, of the points on the boundary of our domain, and what the boundary conditions are, what's the input flow, what's the pressure on the boundary. Outputs, if we're thinking of a finite volume problem as being our ground truth, the outputs might be what is the value of the components of velocity at each point, at each volume, what's the value of the pressure at each volume. Or the outputs might be some quantity that's derived from that flow field. So for example, actually what we're often interested in is not what the entire flow field is, but what's the flow at the outflow boundary, or what's the total amount of drag around some body in the middle of the flow, or what's the lift. So the output might be the entire flow field, or it might be some quantity which is a derived quantity based upon the flow field. And so the idea is that we have a set of inputs X which are taken sampled from some probability distribution P. So what does that mean? That just means when we're doing this approximation, we'll have a set of flow conditions that we're interested in. Okay, so we will have a range of geometries, we'll have a range of boundary conditions associated with those geometries, and we're going to sample from within that range based upon some probability distribution. And associated with those range of inputs, for each sample within that range, we will assume there is a specific output Y. And the objective here is to try to approximate the relationship between X and Y using this function phi. And this function phi will have a lot of parameters associated with it that we can choose to try and make phi the best possible approximation to the relationship between X and Y. Okay. And the way we'll do that is to try and minimize something. So in the paper, they call it a risk functional. So we're going to say, let's assume that there is some objective L, which relates Y, the true output, to phi, the output of our learning machine. This might, for example, be the L2 norm of the difference between between Y and phi. So L is some loss function. And we're going to try and minimize this loss function across our probability distribution, and that's what we call the risk functional. And we're going to do a minimization of this in order to try and choose the parameters W, which make this risk functional as small as possible, and in that sense make phi as good as it possibly can be at predicting the true value Y for a given input X. Okay, there's a lot of words on this slide. So let's have a picture. So in this picture here, we're going to assume we have a set of input values that we're going to sample. So this is the range of geometries we're considering in our analogy with a fluid problem, for example. And then we've got this system, and this is basically my ground truth. So this system you can think of as being, again, to stick with the analogy of computational fluid dynamics, the system might be a black box CFD solver, ANSYS Fluent, for example, and the system takes as its input all of the boundary conditions and the geometry, and it produces as its output the flow field at each point in our high fidelity mesh. So this is the truth, and the idea is we're going to try and replace this, because this can be very expensive. If you think of a CFD calculation with tens of millions of elements in 3D. I'm sure those of you doing Alan Burns coursework at the moment will know how long a really high fidelity flow calculation can take. So we want to replace this with just some function phi that we're going to learn in some way, which approximates this. And depending on how we use our knowledge of this system in order to define phi, and in particular to train the parameters of phi, which I'm representing as W here, this will either represent what we call supervised or unsupervised or semi-supervised learning. So in the case of supervised learning, the idea is we're going to use this system a lot. We're going to have a whole set of inputs X. We're going to use this system to compute a whole set of corresponding ground truth outputs Y. And we're going to use that vast amount of ground truth data in order to choose the values of these parameters W in order to make phi, my learning machine, the best possible approximation to this system. So that's what we mean by supervised learning. The other extreme would be unsupervised learning, where we don't use the knowledge of this system in any way in order to determine phi. So that might sound a little bit far-fetched, but the way we might imagine how that could work is that phi could be some function which has as its input the input parameters to our flow problem, as its outputs Y, an estimate of what the flow field is at each point on our mesh, And then what we minimize in order to calculate phi is a residual of our discrete Navier-Stokes equations. And so instead of solving the Navier-Stokes equations, we just try and find some function which minimizes the residual of those equations, where x and y are given inputs. So x is the input field, y is the flow field, and we want to try and minimize the residual. And obviously, if we can get a zero residual, then we are satisfying the Navier-Stokes, the discretized Navier-Stokes equations, and so we can say that's a good approximation. If we have a small residual, then we hope that's a good enough approximation. So you can imagine, a scenario like that where we don't use any information, we don't use our fluent or our ground truth at all, but we still devise a network. I'll tell you what I mean by network in a minute. We still devise a learning machine which is capable of trying to find that relationship between the inputs and the outputs. And then semi-supervised learning, as the name suggests, we don't rely on this system in order to train all the values of W, but we have access to this information in order to influence the quality of this approximation function. So I've given you a very quick sort of overview of the different terminologies that are used. I've tried to give you a sense for what we're trying to achieve, which is define this function phi, which accurately represents the true relationship between our inputs x and our outputs y. So what I'm going to do now is give you some more specific examples, which I hope will make it a little bit more understandable. Before I do that, I'm going to pause and ask if anybody has a question. If you have a question, just unmute and ask it now, please. Okay, in that case, let me go on to talk a little bit more about supervised learning. So, as I've already said, supervised learning implies the availability of the corrective or ground truth information to the learning machine. And in its simplest form, what that means is so-called labeled training data. So in its simplest form, that means that for a whole set of input values x, we have the corresponding true output values y. And that's what labeled data means. So given every input in our training set x, there's a corresponding true output y. And again, in the case of our fluid dynamics analogy, that true output y might be the output of a 3D very fine mesh ANSYS fluent simulation. Now, we might have 1,000 sets of input variables, so 1,000 different boundary conditions or geometries, and therefore we have to run Fluent 1,000 times in order to get 1,000 corresponding output values, which are the flow fields at each point in the finite volume mesh. So it might be quite expensive to get a large labeled training data set, but supervised learning assumes that we have one. And then the idea is we use that to minimize the cost function. I've called it a cost, well, they've called it a cost function here, but on the previous slide, I think they refer to it as the risk functional. So a bit of inconsistency there. But the idea is we're going to minimize something in order to try and get our learning machine to give us the best approximation. So the most commonly used loss function in that minimization is, as I mentioned earlier, the L2 norm of the difference between the true solution y and the machine learning approximation of that true solution over the set of labeled input values in the training data set. So to go back to my analogy, if we've got 1,000 sets of boundary conditions and geometries, and for each of those thousands we've calculated what the true flow field is, true depending on our CFD calculation, then we would take the sum over all 1,000 inputs, calculate what phi is for a given set of parameters w, and then subtract from that the true solution, and then take the sum over all of those values of this 2 norm. And the idea is we're going to try and choose these parameters w, which are part of the definition of our function phi, in order to minimize this loss function over all of our training data set. And the hope is, if we can make phi be a really good representation of the relationship between x and y in our training data set, then it will also be a good relationship between an unseen x and the corresponding y. where X is an unseen set of boundary conditions and initial geometries. So this is the idea, and again, I'm going to show you this in a little bit more detail in the case of something called a feed-forward neural network. So one of the most common approaches to approximating these learning machines is to use so-called neural networks. I'm sure you've heard the terminology before. And I'm going to show you one specific example of a neural network here, which is a so-called feed-forward neural network. And the example I'm going to show you is even more specific than that. It's what I call a fully connected feed-forward neural network. So I'm going to try and show you what a neural network is and then relate it back to this idea on the previous slide, just to make that clear in the context where phi is represented by this neural network. So the idea is we need to define a function phi. And this function phi is going to have a number of parameters. And we're going to choose the parameters which make this phi the best possible approximation to the true relationship between the inputs x and the outputs y. And in this case, my nonlinear function is going to be defined through this network of nodes in a graph. And the idea is that we're going to have a so-called input layer. So this input layer has a number of values to it. So think of this as a vector, as I've shown it on this particular diagram, which is there, figure 7. This is a vector with 5 values in it. So this is assuming we have 5 inputs to our problem. So we're defining, for example, the boundary conditions to our flow problem based upon 5 parameters. And based upon those 5 parameters, we're uniquely defining what the boundary conditions are to our problem. And then the output layer is a vector which will contain a value, a set of values which define the output flow field. So in our flow problem analogy, maybe there's a grid, let's say, with 100,000 finite volumes in, and for each of those volumes, our output is going to be u, v, and p at the center of that volume. So this might have 300, this might be an output vector with 300,000 values in, and this input vector, as I say, as we've shown here, is 5. On the other hand, our output vector might be something completely different. If we're only, for example, trying to predict, let's say, the drag and the lift around an object in the interior of the flow, our output layer might just have 2 values, the drag coefficient and the lift coefficient. So the output layer will vary depending on what it is that we're trying to get our learning model to predict. And then in between that, we've got these so-called hidden layers. And so these are just vectors of values that are computed in a certain way. So the analogy that we use in a lot of the language here is associated with neural networks, biological neural networks in the brain, because that's what motivated these particular types of learning machine. So you'll see terminology like these are layers of our network, but you can just think of these as vectors of values. And then each layer has a number of so-called neurons, but you can just think of these as values in a vector. And the idea is that we're going to have each of these neurons will have a set of inputs, and then in this example, which is a fully connected layer, each neuron will have as its input the outputs from each of the neurons in the previous layer, and it will combine all of those inputs and produce a single output that it will then pass on to the next layer. Okay, so the purpose of each neuron is to do a very simple calculation, to combine a set of inputs in some particular way to produce a single output and pass it forward, hence feed-forward neural network. And it turns out that if we define a general way of combining these things, let's say, for example, a linear combination of all of the inputs, and then we apply some function to that linear combination, it turns out that this approach gives us a very, very rich and complex family of nonlinear functions. And that family of nonlinear functions is defined by the parameters that we use to do the combining of these inputs at each neuron. I'll show you this in a bit more detail. And there's a theoretical result called the universal approximation theorem, which basically proves that I can approximate any nonlinear function with, say, m inputs and n outputs. I can approximate any nonlinear function with m inputs and n outputs to an arbitrary accuracy using a sufficiently deep neural network such as this. So with enough, as long as I've got enough layers and enough neurons in each layer, I can approximate any function to arbitrary accuracy. So a very powerful theorem that shows this family of nonlinear functions is universal approximator. Okay, so I've talked in the abstract. Let's just be a little bit more precise. So in this specific example, what is x, what is phi, and what is w? Well, I've already talked about what x and phi are. They're the input layers. So x is just a vector of values corresponding to a numerical value for each node in the input layer. So if I have 1,000 inputs, my input layer is 1,000. If I have 5 inputs, my input layer is a vector of size 5. And my output layer, that is my prediction. So again, to go back to the flow field example, if I have a flow field with 1,000 collocation points, then my output layer will be 3,000 points because I'll have u, v, and p value at each point. So what is phi and what is w? Well, phi is the nonlinear function that we get by doing as I just described, taking each of these inputs, passing to each of these neurons the values of the inputs from the previous layer, combining them in a certain way to produce an output. And basically, each of those is a little function, and the convolution of all of those functions, one after another, some of them in parallel within the same layer, defines a really complex and rich nonlinear function with lots and lots of parameters in it. So here's what happens at each individual neuron. Here's the what we do. So think about node I in layer n. Okay. So remember, the inputs to node I in layer n is the outputs from everything in the previous layer. So I'm going to say xin is going to be the output that I calculate at node I in layer n, and xjn-1 is going to represent the outputs at node j in layer n-1. Okay, so if we look about the first layer here, the previous layer had 5 values to it, so j would run from 1 to 5 or 0 to 4. Here, if this layer has 1,000 in it, then in this case, when we look at a node in this layer, j would run from 0 to 999. Okay, so the sum over j is the sum over the total number of nodes in the previous layer. And basically, I'm going to combine all of those inputs by taking a linear combination plus some constant value. So this is an affine combination of all of the node values of the previous layer. And that linear combination or affine combination is going to produce a single number z. And then I'm just going to apply a simple activation function, as it's called, to that value z. That could be the identity, by the way. So f could just be the identity function, in which case all I've got is just a linear combination of the inputs to produce the output at each node. But normally it's a nonlinear function. Typical examples of the so-called sigmoid or hyperbolic tangent function. And so there are reasons for that. The important thing to emphasize about both of these functions is that they're differentiable, and I'll come back to that later. So the idea is, at each node, we take a linear combination of all of the inputs, we apply the function f, the activation function, and it produces an output, which is then passed on to each of the nodes later at the next layer of the network. And this happens at each of these nodes. So for each of these nodes, I need to define the value of w, I, j, n. Okay, so w, I, j, n is effectively a weight associated with this link, okay, where this is j, this is I, this is n. So layer n, node I, and it's linked to all of the nodes j equals 0 through to the maximum number in the previous layer. So there's an awful lot of parameters, w, I, j, n, that I can choose to define this nonlinear function phi. And the idea is I'm going to try and choose those parameters w to minimize my loss function associated with this phi. So if we go back to this loss function, I'm going to try and choose w so that the sum of the squares of the error between the true value and my predicted value is as small as possible across the whole of my training set. Remember, I talked about maybe having 1,000 values of the inputs for which we've computed the true value of the output. So what we try and do is choose the values of w, all of these weights, so as to minimize some objective. And this, as I say, is a very common objective function, the sum of the L2 norm so k runs over all of the values in our training data set, And for all of the values in that, we try and choose W to minimize this. Now, this is a ridiculously complex nonlinear minimization problem, because W might have hundreds of thousands of parameter values. So this might be a vector with hundreds or even millions of values. And our training data set K probably won't be as big as that. So this is not necessarily even an optimization problem we can solve uniquely. So what we try and do is minimize this, or at least make this as small as possible within a reasonable amount of time, computational time. So this is called the training phase in a supervised learning problem. And there's lots of freely available software that you can use to do this training. And the most common algorithm that's used to do it is something called the stochastic gradient descent algorithm. And what that does is it basically tries to find the derivative of this optimization function with respect to W, all of the vectors W, hence this gradient term. But it's a stochastic gradient descent, so it actually, rather than finding the derivative with respect to all of the parameters W, at each iteration it stochastically picks a subset of the parameters, calculates the gradient with respect to the subset of parameters, and tries to reduce the objective function in the direction given by that subspace. But it uses the fact that that phi is differentiable in order to compute a gradient. And there's a very famous algorithm called the backpropagation algorithm, which allows us to find the exact gradient of a feed-forward neural network in a very efficient way. So we can get the gradient efficiently, provided we made sure that our activation functions F are themselves differentiable functions. Okay, again, I'm going to pause. Any questions on what I've just covered around feed-forward networks? This is taking me way longer than I'd hoped, so I'm going to have to skip some bits of this presentation, I'm afraid, but hopefully it's better to at least cover some bits properly than speed through the whole thing. So let me talk a little bit about unsupervised learning, and then maybe I'll skip through a few bits to the end. So unsupervised learning is the other end of the extreme, where we try to use our learning machine in order to extract information, but without necessarily having reference to the ground truth data. And there are a number of important applications of unsupervised learning in fluid dynamics and in machine learning generally. One of them is something called clustering, but I'm already said I'm going to skip that. But the other one that I'll talk a little bit about is so-called dimensional reduction. So the idea is, can we extract a very low dimensional basis that gives a good approximation to the ground truth system? And so the next slide illustrates that this can be done in a way that's very similar to a standard technique in analysis for doing the same thing, called principal orthogonal decomposition, or sometimes linear principal components analysis. So let me just focus on what's happening on the left-hand side here, okay? On the left-hand side here, what we've got is a set of vectors, xn, where each vector has a large number of dimensions. And so the idea we're going to try and do here is we're going to say, can we represent the space that is covered by this set of vectors xn by a much smaller dimensional subspace? And the way we typically do that using this principal component analysis is we introduce this matrix S, so-called covariance matrix. I've subtracted from each entry X the mean, so it's the covariance matrix of the mean subtracted data. And then we solve an eigenvalue problem to find the largest eigenvalues of S. This is a positive definite matrix, by the way it's been defined. So we know all of the eigenvalues are real and positive. And so what we can do is find the largest eigenvalues and the corresponding eigenvectors. And it turns out that those eigenvectors provide a good approximation. So I've said, let's retain, if D is the dimension of the space, so xn is our, maybe for example, it's, again, to relate back to the flow example, let's suppose we're solving a problem on a finite volume mesh with 1,000 volumes, and so xn might be the velocity field and the pressure field at each of those 1,000 points, so it might be a vector of dimension 3,000. But what we can often say is we can represent the flow field very accurately by a much smaller dimensional space by taking a subset of these eigenvectors, maybe m might be 10 or something like that, just the 10 most dominant eigenvectors. And then if we try to take linear combinations of those 10 dominant eigenvectors, that will give a, generally speaking, a very good representation of the flow field that we've sampled these n flow vectors from. So the idea is this is a well-known approach in approximation theory, this principal component analysis. And what this slide shows you is that a neural network along the lines that I've just described, a very simple version of it, is exactly the same as this. So if we restrict our neural network to something with just one layer, and we let the inputs and the output dimension be the same, and that's d, the dimension of these vectors xn, and if we define an interior layer here of size m, where m is a lot less than d, and if we define our f here to be the identity, so that effectively our activation function is just a linear combination of the inputs from the previous layer, it turns out that it can be proven that this has exactly the same effect as the principal component analysis or the principal orthogonal decomposition. In other words, with this layer here with just m unknown values in, I can represent the space of functions x very, very efficiently, which have a much larger number of parameters. So this is called an autoencoder in machine learning language. But the bottom line is that I can recover outputs x hat, which are really good approximations to x, even though it looks like I've thrown away a lot of information. So this might be a vector with hundreds of thousands of degrees of freedom. This might be a vector with just 10 or 20 degrees of freedom. Reducing this to a much smaller vector makes it look like I'm throwing away a lot of information. But if I then recreate my approximation to that, it turns out that x hat can be a really good approximation to x, even though I've apparently thrown away a lot of information in this encoding phase. So you can think of it like a compression algorithm as well. So we're data compressing something that's got thousands of parameters in to something which has got tens of parameters in, but we can still decompress, decode, and recover something which is remarkably close to the original approximation. So this POD is a really powerful tool in approximation theory, and what we can show using machine learning and unsupervised machine learning is we can train the parameters in order to be able to exactly recover this POD. And that's using just linear activation functions. What this caption says is if we make non-linear activation functions, then we can do even better. We can generalize this to be even better approximation than we get using the principal components analysis. Or we can have something with more layers in. So if we have even more layers in, then we can have even fewer latent variables. In other words, we can compress the data even more efficiently in our encoding step and still recover a really good output. So this is really a slide that says what classical approaches have been doing for many, many years can be approximated exactly using machine learning, but also can be approximated in a way that generalizes it really substantially and makes it a much more efficient generalization using machine learning. So why is that important, for example, in fluid dynamics? Well, for example, we might have a whole load of flow regimes. We could calculate the POD modes using the eigenvalue approach, or we could just use an autoencoder to do exactly the same thing. Now, you'll see these don't look exactly the same as these. This is still a basis for the same space as here, but it's just a different basis. So this actually isn't an orthogonal basis that we get with the principal orthogonal decomposition, but nevertheless, this autoencoder still gives us the same basis as this. And so we can approximate a whole load of flows just by taking linear combinations of these simple flow values here. And the important thing is we can approximate all of the flows within our distribution of flows that we're considering effectively just by taking linear combinations of these principal components. So dimensional reduction, this is kind of a bit of a summary here. We've shown the relationship between the two-layer neural network and the principal orthogonal decomposition, but we've shown that by using non-linear activation functions and more layers, we can have much more generality. And actually, deep learning allows us to do that by having a whole load of layers, but that does mean that there are more parameters to tune. And so the observation that they make here is that although this might work very well in many machine learning applications, there's still an issue in terms of the fact that what we get here is very good for allowing us to approximate flows that are similar to the flows that we've used in our training data set. But if we've got a flow that's very different to the one that's in our training data set, we won't be able to approximate it well. It's not suitable for extrapolation, is what that last bit means. So I've shown you one example of where we can, of how people do use unsupervised learning to do this dimensional reduction. And that's really good because not only does it allow us to represent flows with a fewer number of degrees of freedom, but also when we come to do applications such as flow optimization, it means we can focus on optimizing fewer number of degrees of freedom as well to get a desired flow regime. I'll come back to that in a few minutes. I'm going to just have to totally skip semi-supervised learning, I'm afraid. Just don't have time in the 10 minutes I've got there, because I want to spend a bit of time talking about how we can use some of these ideas to do flow modeling. So the first example here I've got is effectively repeating what the analogy I've already used when I talked about neural networks. The idea of the analogy I showed you when we talked about neural network is how can we train a neural network to allow us to simulate a flow field based upon a training data set of some specific inputs with some labeled outputs which represent the true flow field corresponding to those inputs. And if we get that right, we can provide a learning machine that allows us to replace the CFD solver with just the learning machine. And why is that better? Well, it's better because it's actually, if we go back to that neural network example, it's actually really quick to evaluate this nonlinear function. It's just a network of really simple operations. I take the values here, I combine them here and produce an output. What's more, I can do all of that in parallel. I can calculate what happens at this node simultaneously with this node, simultaneously with this node, etc. So at each layer, I can calculate these things completely independently of each other. And so that's really good for implementing on a parallel computer or a GPU or some other device. So basically, it's really fast, given a set of inputs, to flow through this network and get the outputs. It takes a fraction of a second, as opposed to many minutes or hours to do an entire CFD solve. So if we can make that work, we can replace simulating an entire flow by one evaluation of our learning machine and get an answer in a massive fraction of the time. But it's really tough to make that work, actually, because we don't usually have enough training data and we don't usually have a rich enough neural network to do that effectively. So that's a real challenging open problem in fluid dynamics. Another area that's quite important is so-called super resolution. So predicting features of a flow at a finer resolution that we can measure. Let me give you a tangible example. Fergus, excuse me, I'll take a quick drink. Fergus Schoen is a student in the year above you. He's working on problems where, right now, he's looking at a problem where he's got some imaging data from a technique called 4D MRI. And the resolution of that, and he's trying to model flow in the ventricle of a heart. And the resolution of that is like square cubes of maybe 2 by 2 by 2 millimeters. And what he wants to do is take that resolution and get a finer resolution flow so that he can then, with accuracy, estimate things like what is the wall shear stress on the boundary of the ventricle. And so the way he'll do that is to take as the input this coarse resolution flow and then use a neural network to try to simultaneously match the coarse grain resolution that's observed, but also satisfy the Navier-Stokes equations at a finer level, but do it very efficiently, not do a full CFD solve, and match that fine grain solution so that you can get a much finer resolution flow that matches the observations, but also satisfies the underlying PDE model. That means that we believe that it's a true representation of the flow. And then he'll be able to use that to calculate this wall shear stress and the other things he needs to do as research. So with super resolution, we've got observed data, but we really want to get a finer understanding of what the flow is. And not unrelated to that, machine learning is used quite a lot in turbulence modeling as well. Same thing, we've got something that we're able to calculate at a particular resolution, and what the turbulence model does is it captures the finer resolution aspects of the flow, and so we can try and use machine learning to do that in an efficient way. And I've already talked about the classification problem as well. So the approach that Fergus is using is something called a physics-informed neural network. So his neural network is going to try to ensure that the physics of the flow at the fine resolution is captured. So the neural network effectively will try to minimize the residual of the discrete Navier-Stokes equations at that fine level, but simultaneously it will also minimize the difference between the observed data and the fine flow field at the coarser level. So this is an example of what we call a physics-informed neural network, and this is a really important open area with loads of research possibilities in fluid dynamics at the moment, how we can combine machine learning, but in a way that doesn't treat these things as a black box, that really understands what are the physical important things that the outputs y or y hat have to actually respect, because we want the y hats to, for example, ensure conservation of mass, to ensure that we don't have break the second law of thermodynamics, etc., etc. So how can we do that? This is a really important, challenging, open problem. The paper also talks about another interesting and challenging problem around long short-term memory networks. Well, I'm really short of time and I'd love to talk about this in more detail, but this is basically, I've talked so far only about steady state problems, but of course most flow problems of interest are time-dependent problems, and so really what we're trying to produce is an entire time sequence of outputs. And what we could do in a naive way is say, okay, if I know what the flow regime is at time tn, can I use that to use a neural network to produce an estimate of what the flow field will be at time tn plus 1? What that misses though is you only got a snapshot at one time to produce forward. If you were to use the flow field at earlier times, for example time tn minus 1, then you could look at the difference between the flow between tn minus 1 and tn to see how it's changing. So as well as using what the flow is at tn, we can also use how it's changing in order to get a better approximation of the future. And so what long short-term memory networks do is they're a sequence of networks that relate what's happening at one time level to the next in our time series, but also allows to have network links jumping from one time level to 2 or 4 in the past. And so they allow us to do these time sequences in a more sophisticated way. Again, really powerful, but also lots of open problems and challenges about how we can get time sequences in there. One, for example, is thinking about, if you think about a compressible flow problem, you might do something at, you might compress the flow at one part of the domain, creating a wave that travels through the flow. So at a later point in space and a later point in time, we have that impact of that action. So how can what's happening at a later time use the memory from what happened in the earlier time, and how can we combine those things together in a way that's effective? So really, really interesting and challenging problems there. Other areas where we can apply neural networks are around flow optimization and control. So flow optimization is trying to minimize or maximize something. Flow control is more subtle. We might want to, for example, split a flow into 2, but have equal mass going down each pipe. Or we might want to make sure that the temperature range of a machine is never exceeded, so we always the flow always stays within a given temperature range. So there's all sorts of things we might want to do to control the flow. In the 2 minutes I've got left, I think I'll just say that a really common way of doing that is to use machine learning to give us what's called a surrogate. So, and this is something that Fatini in her 4th year is working on in her PhD project in the CDT. So she's trying to solve a problem where she's trying to optimize DNA amplification in a flow device. And what she does is she has a high fidelity solution that she computes in COMSOL, but she's also got a machine learning model, which is what we call the low fidelity solution, that gives us an approximation to that very expensive COMSOL solver. And so what you can do is, instead of optimizing where your cost function is based on the output of the high resolution flow solver, you use your surrogate, your machine learning model, to do the optimization, and then you just refer occasionally to the high fidelity model just to ensure that you're homing in on the right answer. So this is a way in which we can do flow optimization by using machine learning. Okay, I did say if I got time I'd talk about reinforcement learning, which is a semi-supervised approach, but I'm afraid I haven't got time. I'm going to skip over that. So in terms of where we've got to with discussion and outlook, basically this paper that I've used as the basis for this presentation highlights a whole range of areas where we can use machine learning to solve fluid mechanics tasks. And I've highlighted actual flow resolution using machine learning, but also things like dimensional reduction, feature extraction. It says PIV processing because I'm quoting from them, but I've used the example from Fergus's work of 4D MRI. But any image analysis where we want to process those, we can use machine learning. And in particular, we can do things like super resolution. We can do reduced order modeling, turbulence, shape optimization, flow control. So machine learning has a lot to do, a lot of opportunities to do in fluid dynamics. I'm going to skip over things and just jump to my final slide, which is their future issues slide. So these are some of the open problems in machine learning for fluid dynamics that have been highlighted. And I haven't got time to talk about all of them, but I'm going to just talk about number 2, because I've come back to this, how we can incorporate and enforce flow physics with the data-driven analysis that we get from machine learning. And combining hybrid algorithms that are data-driven but incorporate flow physics, for me, is one of the really exciting open problems at the moment. So the PhD topic that I'm putting forward in the booklet that you'll get at some point in the next week and a half focuses very much around how we can develop new flow algorithms that hybridize data-driven methods with flow physics. And I have stopped just about on time.